Okay. All right. Good morning, everyone. We have reached a milestone here in our course, beginning our review of analytic geometry. And most mathematicians and virtually all historians of mathematics agree that there would be no modern mathematics as we understand it until this invention of analytic geometry. It is one of the key points in the development of mathematics. Certainly, calculus is the foundation of all of modern mathematics, and there would be no calculus. There can be no calculus without the concepts of analytic geometry. So we truly have entered here into with our functional point of view. We certainly have entered into pre-calculus. Analytic geometry is interesting. It's different from the synthetic geometry of Euclid. You know, the geometry that we studied in 10th grade. Many people loved 10th grade geometry, but many people found it difficult, frustrating, because it doesn't have the algorithms that algebra has. You'd be given this diagram and be given a statement of a theorem and told to prove it, and it wasn't clear very often just how to begin. Obviously, for some simple theorems, it was, but for many, it wasn't clear just what to start with, how to begin the proof. And certainly when you studied some of the proofs, some of the more interesting proofs, some of the famous proofs come, in the development of geometry, you wondered how you followed the proof, that was fine, but you wondered how they thought of, drawing that line or making that point or making that point of view. It's very different, and so that makes synthetic geometry very challenging. And almost every proof is different. You have to start all over again with finding some kind of a clever idea. It's not the case with analytic geometry. And in fact, this is the point that Descartes himself made as he developed analytic geometry. We find his development of analytic geometry as an appendix to the famous discourse on method. He writes 3 appendices to that philosophical work, considered the beginning of modern philosophy. And one of them is this geometry. And he makes the point that this method is not new geometry at all. It's a different way of approaching geometry. It's a different way of forming the problems, forming the investigation questions about a geometric situation, turning them into algebra. And he says this is a much simpler, in a sense, way to go, because if you can turn those geometric relationships that you're interested in trying to study into algebraic relationships using my method, the algebra will suggest where to go. The algebra will suggest what to try. And as you begin to build up a bigger and bigger toolbox, as we will hear in this class about that kind of conversion from geometric concepts to algebraic concepts, as that toolbox grows, then you have more and more powerful methods at your disposal, algebraic methods, to investigate more and more complex geometric situations. And I guess the best example, the simplest example of the truth of that is for the first 2,000 years of the history of mathematics before analytic geometry, we really didn't get much further than the methods of Euclid, which are basically the point, the line, and the circle. Oh, sure, there were a number of important investigations of the conics, for example, and Archimedes' work on spirals, etc. But it really almost didn't much more than touch the surface of those subjects. It really took the methods of analytic geometry before we could truly expand beyond the straight line, beyond just a simple circle, to very general curves. And so we'll get started with that development this morning. Okay, we begin with the Cartesian coordinate system, the XY graph, known as the Cartesian plane. And in fact, an alternate name for analytic geometry is Cartesian geometry. And it begins here with naming points, the most fundamental element of Euclid, with numbers, okay, with the basic xy plane that we're familiar with. And we just here take a look at some of those points, like for example, going out on the x-axis, having 1, 0. The x value is 1, but the y value would be 0. And on the y-axis, 0, 2, and a point, for example, down here of -2, -3, and coming over here of -0.5 up to 1, etc. This I will assume everyone is familiar with, be able to read points on a graph. We can go a little bit further, though, and start to look at families of points. And here's an interesting family. All these points have something in common. They all have a y value of 2. Well, you could state that, right, as an equation. You can say, well, all those points have the property that y, the y coordinate, is equal to 2. In fact, that's a function, right? Y is equal to a function of x is equal to 2 is a very simple function. The functional value, no matter what x you give me, is always 2. It has a perfectly nice table of values where all the bottom values are 2, and it is a perfectly nice constant function. And of course, we can take all the values on the Cartesian plane who have a y value of 2, and we get our first line. So we get into now the second, very simple way, of course, the second fundamental object of Euclidean geometry after the point is the line. We can do the same thing characterizing all the points in the plane, for example, that have an x value of -1. That also can be characterized by an equation. X is equal to -1 characterizes all those points, and all the points on the plane like that, another line, a vertical line. This is not a function, right? Because x we think of here, as we look at the Cartesian plane, x is the independent variable and y is the dependent variable. We're always looking at y as a function of x on a plane like this. And so this is just one value, right? One input value, and you get, you know, an infinite number of possible y values. So this is not a function. This breaks about every way possible the definition of a function. If I would ask you for the function value of -1, which is the only value that this function takes on in the domain, it can be anything. Well, that's exactly what functions can't do. They must give us an unambiguous value for the y value. However, it is a valid equation. X is equal to -1 very much characterizes that line. So we see that horizontal lines can be written as functions, but the vertical lines cannot. And we'll see that the vertical lines are the only lines that can't be written as a function. All the other lines on the plane that we will draw, which we'll be covering this morning, this will be our almost entire focus this morning, will be the straight line and its properties. All the other lines can be written as a function of x. We start, however, with the distance formula. It all begins with this. I have scattered a bunch of points here, and if we ask for the distance from A to B, you can see that A has an x value of 3, and B has an x value of 6. There's no change in y. And so the distance from A to B would be the 6 minus the 3, which is 3. We always want distance, by the way, to be, you know, to be positive. Actually, I really should use a better word than distance actually would be length. We always want the length of these lines to be positive. Distances actually can be negative, but the distance formula always calls for positive values. So when we talk about the distance between 2 points, we're also talking about the length of the line segment between those 2 points. And then we can just run down and look at the various other distances between C way out here at -4 and that B here of 6. We see that there's a distance here of 10. We're literally adding up these negative numbers, right? Here's a length of -4, here's a length of 6. The total length here is 10. The distance from the origin is very simple. The distance is always the value. So the distance from O to C would be 4. And finally here, the distance from D to E, right? D has the x coordinate x1, and E has the coordinate x2, and we can say algebraically that the distance from D to E would be x1 minus x2. Okay, we want to use the x1 first because that's what will give us the positive difference, taking the positive number first, and then the negative number, and Y the same. So it's easy enough to find the distance between points along the x-axis, to find the distances along the y-axis. Basically, it's the difference between the coordinates. And you always want to choose the larger coordinate first in taking that distance so you get a positive length. Being a little bit more ambitious, if we wanted to find the distance between E and F, now we have a line that's not on one of the axes. Looking for the distance from E to F, well, of course, the trick is to use the Pythagorean theorem. And yes, the whole Cartesian plane ultimately is based upon the Pythagorean theorem. So we can certainly say in a very naive way that the distance from E to F squared is the distance from E to O squared plus the distance from O to F squared. But those distances we've already calculated. We know how to find the distances along the axes. So that would be x2 squared plus y1 squared. So a little bit deeper waters. Finally, if you wanted to write the actual distance, not the square of the distance, you take the square root of both sides. And so yes, the distance formula is characterized by a square root. And finally, if we take two arbitrary points, call them U and V, and writing their coordinates as x sub u and y sub u, and the coordinates of V as x sub V and y sub V. It's a very standard kind of notation that's very often used in analytic geometry to identify the coordinates of the point V. We want to find the distance between U and V. We want to find the line, the length of the line segment UV. We would use the same trick, right? We would go ahead and use Pythagorean theorem. Here, of course, we have to find that intersection point W. Well, for now, let's just call it x sub W and y sub W. So again, we can very naively just write down the Pythagorean theorem. We can say the distance or the length UV is the length UW squared plus the length VW squared. Okay, that's just a statement of Pythagorean theorem because our line segments are along the axes. I could go one step further and actually use the coordinates. And so there would be the coordinates that we've used up on top there on the upper right, just using that principle, that the distance from U to V, we notice that going from U to, distance from U to W, and the distance from U to W, we notice the Y value doesn't change. The Y value is, whatever the Y value is. It's only the change in the X value that gives us that length. So it would be X sub U minus X sub W. And when we look at W and V, we notice that the X values are the same. XW is in fact the same as XV. So the only thing that's changing is the Y values. So to find the distance from V to W, we only need to take the difference of the Y values. Finally, we make that observation, right, that the X coordinate of W is nothing more than the X coordinate of U. It's, I'm sorry. Did I say that right? I'm sorry, I did say it wrong. The X coordinate of W is nothing more than the X coordinate of V. They share a common X value. And similarly, the Y coordinate of W shares the same as the Y coordinate of U. It's simply a line parallel to the X axis. So now that we know that what W is in terms of our endpoint coordinates, we can rewrite that equation, more recognizable as the distance formula. One more change, I'll just kind of line up the U's and the V's, and we see that the distance formula is the difference of the X coordinates squared plus the difference of the Y coordinates squared. And again, using the Pythagorean theorem, we've got to apply that square root. A very important formula. We'll use this formula all throughout the morning. Okay? The distance between 2 points is nothing more than a function of the actual coordinates of those endpoints in that way. The difference of the x coordinates of the endpoint squared plus the difference of the y coordinates squared, taking the whole square root. Before I stop for questions, let's just use one application of the distance formula and get the midpoint formula and see kind of what I'm doing here as we build up our toolbox. Looking for the midpoint of this line segment, AB, looking for that point there, M. We'd like to find a algebraic relationship that could characterize that value M from the values of A and B. Okay. Here I've written the coordinates in a more conventional way of x1, y1, x2, y2. This is more familiar with the equations that we will derive. But I've taken two particular points. Let's say A is 3, 4, and B is -1, -4/3. I needed that -4/3 if I wanted to go through the origin. We'll see that why that's the case in life. You just can't pick up any old points and have them go through the origin. So how do we do this? Same trick. We go ahead and rely upon that right triangle of Pythagoras. And I think you'll agree that if that point here is the midpoint of this line segment, and this point here is the midpoint of this line segment, then that should characterize the midpoint of our line. And in fact, what you're looking at is a very important theorem of Euclid. That if you have a triangle, it doesn't even have to be a right triangle. This happens to be, but we don't even need that. If you have a triangle and you have a point on the midpoint of one side, and you draw a line parallel to the base, you will hit the midpoint of the other side. It's a theorem right out of Euclid, just as the Pythagorean theorem is a theorem right out of Euclid. As a matter of fact, we can't be surprised as we build up this initial toolbox of algebraic relationships about geometry, we keep going back to theorems of Euclid. Essentially, what we're doing by hook or by crook is we're turning the theorems of Euclid into algebra. That's actually what we are doing, because we'll continue to go back and rely upon the geometric relationships found in Euclid as we develop our algebraic relationships. And if you turn your head sideways, you'll see Euclid's theorem again. Here we have a line here with its midpoint, and it's parallel to the base here, and yes, it will hit the midpoint of the side. So this does characterize the midpoint M, and all we need to do is to characterize those particular points. We know how to characterize W. We know that W shares the same X value as A. We know that W shares the same Y value as B. And so in terms of V, well, they share the same X value, so that's 3. And what is the Y value of V? It's just the average of the two Y values of A and B. There's a high point and a low point. To find the middle, you just take the average of those two numbers, 4 and -4/3. Add them up, divide by 2, and you'll get 4/3. You'll get a positive 4/3. The same thing over here. Looking here, the U value, the midpoint, is nothing more than the average of the X values of B and W. We have -1 and 3. We add them up to get 2. We divide by 2. I'm sorry, we get a -2, and we divide by 2 and get 1. 2 over 2 is 1. The Y value does not change. The Y value of both U and W share the same Y value as B because of the parallelness of the line. And so there's our midpoint formula, kind of familiar formula. The midpoint of a line segment is nothing more than the averages of the two end coordinates. So here we have two formulas with both our functions of the endpoint coordinates. Exactly what we would like to do as we build this toolbox. You give me the points, you give me the endpoints of the line segment, I'll tell you the length of the line. I'll tell you the distance between the points. You give me the points, you give me the endpoints of the line segment, I'll be able to calculate for you algebraically the midpoint of that line. It's turning these things into pure algebra. And we'll be doing this basically all morning. getting into more and more interesting lines fundamentally. So let me stop here with these two fundamental formulas and ask if we have any questions so far.
Nothing in the chat yet, Peter.
Okay, well, let's,
You did break up a little bit at one point, but you came right back.
okay, great. Let me know if it gets really bad and I'll turn off the video. I'd like to keep it on if it's possible.
Okay.
Okay, let's get a little deeper now. Let's move into the more general line. Let's do it in two stages. Let's first of all take the line that goes through the origin. We can do vertical lines, we can do horizontal lines. But let's now move into the general line by first of all going through the line that goes through the origin. Turns out that those lines are functions, and in fact, they are proportions. What is a proportion after all? We learned about proportions, I think, like in fourth grade, you know, A1 is to B1 as A2 is to B2 kind of thing. All that it means to say that y is in proportion to x is to say that y is a multiple of x. That's it. That's what a proportion means. If y is going to be a multiple of x, then certainly y is a function of x. Y will depend upon x if it's a multiple of x after all. And so a proportion is simply the characteristic function of mx, where m is the constant of proportionality. I think most of you know why I'm using m. I didn't pick it arbitrarily. This letter, of course, will be the letter that we're going to use. So there's the form of a proportion as a function. Y is equal to mx, where m is that multiple constant. We can go back to when we first learned proportions. We would say that if y is proportional to x, we could say that y1 is to x1 as y2 is to x2. Yeah, you could also even say it the other way around. You could say y1 is to y2 as x1 is to x2. Notice that's just the cross multiply of that guy, algebraically equivalent. So that would be true for any proportional pair. You could take two pairs and write them down as a proportion. And we often use this kind of an equation to solve for one of the unknowns. We've done this, like I say, you know, basically since fourth grade. Take an example of why what's behind this cross multiply, why in fact these ratios, you know, why we can write down these fractions like this. Well, let's take an example to see why. Let's take a very important proportion, the equation of a circumference of a circle. We're told that the circumference of a circle is proportional to the radius. The proportionality is 2 pi. The circumference is equal to 2 pi times the radius. Well, therefore, what is C over R? Given any valid C and R for a particular circle, C over R is equal to 2 pi. Just go ahead and divide both sides of the circumference formula by R. You'll get C over R is equal to 2 pi. So any C over R is always equal to 2 pi. So if we have two different circles, the circumference of one over its radius must equal the circumference of the other one over its radius. And there's our fourth grade formula for proportion. We're simply setting it equal to that proportional constant, in this case, 2 pi. We know the proportions are everywhere. They're everywhere in nature. I literally took these almost at random. It was very easy to write them down. We have Newton's second law of motion, the beginning where classical physics starts. We have E equals mc squared pulled out of special relativity. We have Ohm's law for circuits, that V is equal to IR, the voltage is equal to the amps times the resistance, the current times the resistance. We have Hubble's law, which I'm actually going to use in a minute, that the receding velocity of any galaxy from us, or from any other point in space for that matter, is proportional to the distance away. So the further you are away from us, that galaxy is moving faster and faster. The speed is proportional to how far away it is. And finally, our favorite formula, distance is equal to speed times time. So we were looking at this particular proportion of d is equal to 4t, where clearly 4 would be the speed, and it has a nice table of values. And the point I want to make is if we took a look at that proportion value of y over x If you take any values from the table of values, for example, -8 over -2, looking at that table, -2, 8, -2, -8, or if you took at 520, where the 20 over 5, or even if we stressed it, if we took the general t, where its functional value was 4t, clearly in each case, we keep getting 4. We keep getting that multiple. Okay, that's not surprising. That's what we just set up top. What may be a little bit surprising is if we take any 2 points, I took 2 points at random, -2, -8, and 510, 520, I'm sorry. And we looked at the difference between the y values divided by the difference in the x values, not the x and y
Lost you
values
again, Peter.
themselves.
Can you hear us? Hear
Yes,
me,
I
I
can
should say.
I can hear you, Jenny. Was I breaking up again? Jenny, was I breaking up again? Have I lost everyone? Oh boy, we've got a bad day here. Let's see if
Yeah.
I come back. I just got that message, your internet is unstable. Looks like we're gonna have to limp along here, guys. Am I back? Is my sound back?
It went out for a little bit and you're back now, but you just sounded broken again.
Okay. I
And
don't
now I
know.
can't hear you if you are talking.
I'm talking now. Can you hear me now?
Yes, I heard.
I think,
Yes.
guys, I think the only way to proceed here, I don't know what's going on such a beautiful morning, why I'm getting a bad signal. There's no rhyme or reason that I can figure about the strength of my signal, but what I'm going to do is this, guys, I'm going to just continue on with the lecture, and hopefully the broken pieces will not be too bad. I find that the recording is much better. The recording is not broken. The recording somewhere or other, the sound is always consistent. So I apologize for this, but you may have to just go back to look at the YouTube video to catch some pieces which really you kind of missed because of it's broken. Otherwise, the class will just, the lecture will just fall apart if we keep being interrupted by like this. So let me proceed on, hoping that the signal stabilizes, but I will stop, of course, for questions. We can get a sanity check there, but I think that may be the best way to proceed. All right. So where was I? I was asking the question, if we take any 2 arbitrary points like -2, -8, and 520, and not ask about the difference between their y values and x values, and do that calculation, y2 minus y1 divided by x2 minus x1. You see the difference, as opposed to y2 over x2, I'm now looking at y2 minus y1 over x2 minus x1. I'm looking at the difference of the values, and I find I get the same number. Okay? I get 4, just as I did before. And if I stress it again by taking that arbitrary point t4t and one of the values, like -2, -8, it makes no difference. And I do that calculation again, I'll get an algebraic value at first, but I can factor out, take a look at that algebra, it's very nice. We'll finally get 4 times t plus 2 over t plus 2, which is just 4. And this expression, y2 minus y1 over x2 minus x1, is a very important expression, as most of you recognize. That, of course, is the slope. Okay. Here's a little piece of vocabulary here. This is read delta y over delta x. Delta y is the change in y. Y2 minus y1. Delta x is written symbolizing the change in x. X2 minus x1. These 3 lines here, the 3-line equality sign here indicates that this is a definition. Okay, it's the definition of what delta y over delta x is. I'll use this symbol when I'm defining a new symbol. So what can we do with that table of values? When we plot it, we get a straight line. We're not surprised by that. But as a mathematician, we want to prove that. We want to make sure that that, in fact, is not a coincidence. So no matter what table of values we use, for a proportion, we would get a straight line. Okay? And not surprising, we're going to rely upon Euclid. We're going to take that same trick of creating a right triangle of points, and notice what the change in y over the change in x is here. For I took even a new point. Point is not even on the table. 312. I took a point not even there, but clearly a valid point in proportion. And yes, 8 over 2 is 4. And one of our old points here, taking those changes, a change of 12 over 3, the change is 4. Well, what you're looking at here is another very important theorem in Euclid, that if you have two triangles, don't even have to be right triangles, okay? But in our case, they are, but Euclid's theorems don't even require that these be right triangles. If you have two right triangles where the corresponding sides are proportional and the included angle is equal, then Euclid's theorem tells us that these triangles are similar. These are similar triangles, and what's important about similar triangles is that all the corresponding angles are equal. For example, these angles here, the angles in the lower corner, these angles must be equal to each other because of the similarity of the triangles. And they're similar because basically of this constant proportion that we're finding, this constant ratio of change in y over change in x. It's the constant changing y over changing x is mandating through Euclid's theorems that these angles must be the same. And because these angles are the same, it's an easy step to show that this line is actually a contiguous line, that this is one full solid line. So again, we rely upon Euclid to give us this fundamental idea that a proportion will give us, in fact, a straight line. Obviously, it goes through the through the origin, because 0, 0 is always going to be a point on that in that table of values. If you have y is equal to mx, no matter what m is, if you make x 0, y is going to be 0. So all of our proportions do go through the origin. And here, let's add to our vocabulary here and finally define the slope formulae as that change in y of the change in x. So we find something very important, at least about straight lines going through the origin, that they have a constant slope defined in that way. No matter where you work on the line, no matter what 2 points you pick, you will always get the same ratio, that ratio there, given the name of slope. Okay. Let's take a look at an important example of a changing slope. What you're looking at here is data from two cosmology teams in 1998 who were studying supernova data. Supernovas are, as we know, very, very bright explosions of stars. Therefore, they can be seen very, very far away. And so you can measure things about distant objects by looking at bright supernovas. That's the great advantage of supernovas. They can be seen very, very far away, much farther away than stars, right? The only stars that we can see are in our own Milky Way galaxy. In cosmology, that's our own little neighborhood. It's not going to get us very far. But it's where supernovas can take us out to billions of light years. And of course, we have Hubble's law. Hubble's law goes back to Hubble in the 1920s. Here's a set of data for Hubble's law. You see that the y-axis is redshift, whereas Hubble's law is written as the speed is equal proportional to the distance. The distance is down here in the x coordinate, that's fine. But what's the redshift doing here? I think, as most of you know, redshift can be used as a proxy for speed. The faster something is going away, the faster that ambulance siren is going away from you, the lower the drop of the sound will be. That is the redshift. That change in frequency is what the redshift is. And so, yes, the faster the speed, the greater the redshift. And so you can use redshift as a proxy for speed, and that's what the cosmologists do. It's much easier just to measure you don't measure speed directly, you measure the redshift. So it's just as easy to use the redshift as the y-axis as opposed to the calculated value of speed. You can also use the fundamental data. So that's why we have redshift versus distance for Hubble's law. And you can see the data for stars and also for galaxies, nearby galaxies. It follows Hubble's law very, very nicely. Okay, look at this close piece where the distances are close to us. Follows Hubble's law very, very nicely. What the team found in 1998, two separate teams using two different methodologies of finding this data, what they found was this. They found that their values, their measured values of redshift versus distance began to veer very significantly, very clearly off of our current understanding of Hubble's law, our current measurement of Hubble's law of about 70, the value H0 there, the proportion value was about 70. And they found this clearly veering off of the law. Is this telling us something? Yeah, it turns out it's telling us something very, very important. I just want to go through that argument. So let's take a typical point, measured point, that's not following Hubble's law way, way out there at those great distances. And remember, when we're talking about great distances, we're talking about very far back in time, right? That's the great thing about astronomy. When you're looking at something, you're looking not only at something far away, but you're looking at it in the past, right? The typical one that's always used is you're looking at the sun 8 minutes before we're looking at it now. It takes 8 minutes for the light from the sun to get to us. Well, it takes billions of years. This number here, 3,000, this is 3,000 megaparsecs. It's a little bit over 9 billion light years. Okay? So we're looking very, very far back in time, as well as just distance. So here's a typical value. Okay, this surprising value. It's surprising in the sense that it's not following Hubble's law. Well, if you look at it carefully, we see that it has a certain redshift that we measure. Okay, and we go ahead and take the measured value of the distance. This can be measured. We, of course, have no time to talk about how these measurements are made, how the redshift is made, how the distance is made through these through the study of these supernova. You'll have to take my word for it, that these are measured numbers. And what is surprising is that what we expected, if we expected Hubble's law to continue to hold way back then, that would have been the point. For this particular measured distance there of the blue dot, we would have expected the redshift to be, there, or saying it the other way around. For that particular redshift, we would expect it a closer distance. We would expected the supernova to be closer than we actually measured it to be, which is interesting because if we expected it to be closer, we would have expected it to be brighter, right? Clearly, for any light source, the closer it is, the brighter it gets. That's simple physics, okay? So it was very interesting when the astronomers began to collect this data. The first thing that they noticed is that these very, very distant supernova were dimmer than they expected them to be, okay? But be that as it may, clearly what they found was the expected distance was further away than they expected. Okay. So the distance was further away than what they would expect from Hubble's law. The measured number was bigger. Well, what does that tell you? Well, if you kind of take a slope there, if you take a line which would follow Hubble's law back then, way, way back in the past, 9 billion years ago, because that's how long it took the light for these supernova to get here. Well, if we looked at the universe 9 billion years ago, this would be the rate of expansion, right? That's what H is, right? H is telling us V over D. It's telling us the rate of expansion of the universe. That's the whole fundamental importance of Hubble's law. It's the whole importance of Hubble's constant. It is a measure of the rate of expansion. Clearly, this law, if it is a straight line, in a simple case we can, clearly that H, that slope is lower. That is a smaller number, okay? Fitting that data of very, very long ago. So the Hubble's constant seems to be smaller 9 billion years ago. That means the rate of expansion of the universe was slower 9 billion years ago. Saying it the other way around, very surprisingly, the expansion of the universe now is faster. That is literally the expansion of the universe is accelerating. And this is what was discovered in 1998 by these two teams. They won the Nobel Prize, I think in 2003 for this discovery. I could be wrong about that, but soon after. And this, of course, is what led us to dark energy. The only explanation for this expansion, this acceleration of expansion. Oh, yeah, the universe is still expanding. It's fine. That was expected. It was expected to be a constant expansion. The fact that it's accelerating in its expansion, we have to introduce the concept of dark energy. And we get into all the interesting controversies today about the problems in cosmology. If you're interested, by the way, in this topic, I do have a talk given at my local, the local astronomy group in Vermont, Solvera. I gave a talk back in April about Hubble's constant and the controversies about it. You'll find it out on my YouTube channel. The easiest place to find it, I guess, would be under the channel icon. Look under the Solvera talks, and you'll see the discrepancy about Hubble's constant if you'd like to know more about it. The talk apparently was very well received. It was a talk, directed towards just the educated layman like you guys, not some big highfalutin scientific talk, but it does go into these ideas in more detail. And in fact, I believe this slide is actually in the talk, if I'm not mistaken, or a similar slide. So just to finish off the proportion, before we get into our general line, we can, of course, write that multiple the other way. Instead of being a positive number, that multiple can be a negative number. And not surprising, we'll get the slope going the other way. We'll get a line which is, in the function sense, decreasing. As x gets larger and larger, the y values go down. So this does not surprise us. And if we go ahead and take the slopes and do the calculation anywhere you like, you will get that -3. Okay, so we've added another more general line to our toolbox. Straight lines going through the origin, and we can draw these lines in any angle that we like. We can describe a table of values for it. We can describe a function for it, finding the right multiple. And now let's go to the general straight line and its general characteristics. Okay. Here's kind of the nub of the class. This is the nub of what I want to say this morning, is to characterize the line. Everything else after we do this will be applications of this formula and the other two that we derived, the distance and the midpoint. So we start with our very same proportion that we just had, that -3x, very nice line. And suppose I go ahead and change the function slightly by adding a 4 to every single value. Okay, so I change my function from -3x to -3x plus 4. Well, that'll generate a new table of values. It's simply 4 bigger than the old table of values, 1 for 1. And I'll go ahead and plot those points. And obviously, every single point is 4 higher than the values of the original function. And I don't think I have to convince you that that is also a straight line. As a matter of fact, it's a straight line parallel to the original line. Okay. And I don't think I have to convince you that if you take the slope of that line by taking any two arbitrary points, and I'll take a tough point, I'll take the point t -3t plus 4 with -1 and 7 and calculate the slope formula, sure enough, you will get back the -3. The 4 does not change the slope. The 4 does not characterize the angle that's being made with the x-axis. The 4 only characterizes, actually, well, what it's called, the y-intercept. The 4 just characterizes where it crosses the y-axis. So yes, even for y equals -3x plus 4, the slope remains at -3. Okay? And taking those two arbitrary values, hopefully that convinces you that that is the case. You'll always get -3. The 4 is called Traditionally, the letter that's used is B, and these are the traditional letters, M and B, for this version of the form of the line, M being the slope, B being the y-intercept. And you can see it right here, 0, 4. Okay, the y-intercept is when the functional value of 0, right here, when x is 0, y is 4. And so that is the y-intercept. Y-intercept is nothing more than g of 0, the functional value of 0. The full point being 0, b. The last characteristic we want to mention is, I'm sorry, and the next to last is the actual equation of the line, y equals mx plus b. And that should resonate somewhere, or rather somewhere in the back of your head, because you heard that a million times in your high school math class, if not in your calculus classes. Y equals mx plus b is one of the forms of a straight line. M being the slope, being the y-intercept. A beautiful characterization of the general line. Any line except for a vertical line. Vertical line has that special equation, x is equal to some constant value. Any other line can be characterized by y is equal to mx plus b. Notice if you make b 0, we have where we started with just the simple proportions. With b being 0, all those lines will go through the origin because their y-intercept is 0. And the other thing that we can say with confidence is that if two lines are parallel, it's because they will have the same slope. Okay? We could prove this very formally by going back, dipping into Euclid, and taking a look at the characterizations of parallel lines. But we'll actually look at that a little bit in a minute. But I think this picture is kind of convincing that as you just pick up those points in a constant way, you will generate a parallel line. So, in the spirit that a picture is worth 1,000 words, let me just play with this for a minute, if I may. See, if you think about it, guys, it makes sense that it takes two things to know a straight line. 2 points create a straight line. That's one of Euclid's postulates, that between any 2 points you can draw a line. It's one of his 5 postulates. Apparently, the other way in which we can characterize a line, if we want to do it algebraically, is with 2 other pieces of information, the slope and the y-intercept. That will exactly characterize the line. So there's not a coincidence going on here that it takes 2 numbers, m and b, to characterize a line, just like it takes 2 points to characterize a line. And so here we start with a very simple line. Here I've got a slope of 1 and a y-intercept of 0. And I could go ahead and pick up the y-intercept. I could pick up the b's and notice that the equation is changing. Here is y is equal to x plus 5. I can bring the b down to -4, 3. I can even bring my b's down to negative numbers. Not changing the slope at all. This is just a series, a family of lines which have the same slope as 1, but a different set of b's. And of course, we can characterize this as a whole infinite family of lines, all with a slope of 1 and various different values for b. I can do the same trick here. Say we're going to start with a b of -2. I can begin to play with the slope. Keep the b value at 2, but having the slope now is 2, or the slope of 3, or a slope of 4. And the line is getting steeper and steeper as I change those slopes. And of course, I can play the same game with that slope of 4. I could go ahead and change the b value. My point is, guys, I have complete freedom to draw any line in the Cartesian plane that I want just by picking the b, the m, and the b that I want. The only exception is that vertical line where I would need a slope of infinity. There I lose my functional value, but I still have an equation. I still have the equation. By the way, it's interesting that if I went ahead and made that slope 0, Okay, that's a perfectly nice function. That's a perfectly nice line. That's the line y is equal to 3. Okay, m just happens to be 0. I could go ahead and vary that, make it 4, or 2, or 1, or 0 itself. Y is equal to 0 is the characterization of the x-axis. Any point on the x-axis has a y value of 0. So again, I am characterizing geometric objects as either equations and or functions. Any question about this before we leave this idea? This is really the fundamental idea of characterizing a line in this way. Are there any questions? I hope you're still with me.
We're here, no questions yet.
Okay, I didn't know whether I was talking to myself or not. Thanks, Jenny. All right. I guess wait. I don't think I want to do that. Let me just. Zoom is actually blocking my. Oh yeah, yeah. I think I am going to have to close this thing. Zoom is actually blocking me. I can't get rid of this when I change this. This is terrible. All right. Let me get out of this. Okay. So to summarize, what are the characteristics of a straight line? We'll take our line, arbitrary line. First thing you want to calculate is the slope. Okay, this is the line that we just had, -3. Now, if you take a look at the slope formula is the change in y's over the change in x. Suppose I took any other xy value that's on that line. I got them in red there, red x and red y. If I take any other point on the line, xy, it would also make the slope formula true. After all, it's on the line. And we've agreed that any 2 points on the line fulfill the slope formula. Therefore, I can take one point, x1, y1, a real point that I know, and the general point that I say is on the line that characterizes the line, xy, and I know that that would have to fit the slope formula, that y minus y1 over x minus x1 would have to equal the slope of the line. Well, that is my second characterization of the line. There it is. It's just, there's an equation in x and y. X1, Y1, and M are constants. They're known numbers. They're parameters of the line. It's X and Y are the variables. The traditional way to write that formula is to bring the X1, X minus X1 up and write it, instead of writing as a fraction, the fractional definition of slope, you write it kind of all along one line. And the so-called point slope form is Y minus Y1 is equal to the slope times X minus X1. It is nothing more than the slope formula written along a line where X and Y are characterized as the general point on the line. Very, very powerful form of the straight line. Okay. Notice that here, in a sense, I need, again, 2 pieces of information to characterize the line. I need the slope M and I need a point. Of course, I do need 2 numbers to characterize the point, but conceptually, I still need 2 ideas, 2 things about the line to characterize the line algebraically, the slope and the point. This point, of course, is fundamentally no different than the y-intercept. It's just another point, 0b. It's easy enough to derive from the point slope formula the point intercept form of the line. Here's how you would apply the point slope formula. I have a point -1,7. I have a slope of -3, and just put it in. Y minus 7 is equal to -3 times x minus a -1. That's the, you've just characterized the line. Okay, got to clean up the algebra a little bit. I agree. You don't want a minus. Multiply that minus through, and you can get x minus 7 is equal to -3x minus 3. It's a little bit nicer. And finally, if you really want to go the whole thing, just go ahead and solve for y, and you'll wind up with the other form. You'll wind up with y is equal to mx plus b. Okay? So it's very easy to go, certainly from the point slope form to the slope intercept form. Okay? But that point slope form is a very powerful one. It's a very easy one to work with. All you need to know is any point on the line and the slope, and you can just immediately just write down the equation of the line. Y minus y1 is equal to the slope times x minus x1. The other two characterizations, the y-intercept, which is f of 0, in this case is 4. Looking at the point slope form, it's the slope intercept form, it's obvious. It's the B number. And the other characterization, sorry, there's our 0, 4. The other characterization is the x-intercept. For a function, guys, you always want to know where it crosses the x-axis. It's called the zeros of the function. If you think of it as an equation, it's called the zeros of the equation, or more traditionally, the roots of the equation. You always want to know the value of x that makes the equation, when you set it equal to 0, solves that equation. Geometrically, yes, it's a very, very nice piece in our toolbox. It's the x-intercept, the zeros of our linear equation. By the way, that's why we call these equations linear, because they graph to a straight line. There's where that word comes from. But to find the x-intercept, to find where the line crosses the x-axis, you want to set the function of value equal to 0. What is the x that makes f of x equal to 0? Well, f of x is minus 3x plus 4. It's easy enough to solve for x. And so there is the x-intercept. And I think, no, sorry, I didn't. So there would be the characterization of the line. Okay, you would graph the line. You would at least show the y-intercept and the x-intercept. And I thought, which I don't have, you kind of write up here the equation of the line. Y is equal to mx plus b. And if you wanted to label a line very traditionally, the way we were taught how to label a line in high school, you would label these 2 points, the y and x-intercept, and you kind of write somewhere up above y is equal to minus 3x plus 4. Okay. So classic problem, an important problem to be able to do. Here's 2 points, find the equation of a line and characterize it. So let's go through that. Step one, always step one, get the slope. Take your 2 points, you only need 2 points, apply the slope formula, and you get a slope of minus 2/3. Notice the line is going down. You would expect a negative slope. Okay, so there's my slope, minus 2/3. And now I can immediately write down the equation of the line. No more fuss. Y minus y1 is equal to m times x minus x1. I literally go to the slope and the point slope form. Okay, I just take one of my points. Here I'm taking 3, 2. Y minus 2 is equal to minus 2/3 x minus 3. That is a perfectly fine equation for the line. I can go ahead and clean up the algebra, if you like, by multiplying the minus 2/3 through, solving for y, and getting the slope-intercept form. Y is equal to minus 2/3 plus 4. The other 2 characterizations that we would like the intercept clearly is 4, the b number, and we'd like to find the x-intercept by setting the function of value equal to 0 and solving and getting 6. And there is the characterization of the line. Okay. Why don't you try one? Okay. Try one. They're fun to do. To find all the character. I've left them all blank. The characterizations of this line. Okay. Another exercise, very classic kind of exercise. Find the equation of the line that goes through the point 2 minus 2, and it's parallel to that line. 3y minus 15x plus 21 is equal to 0. Yeah, I'm going to make you work. I'm going to make you solve that equation for y to find the slope. You got to put that equation into mx plus b form, pick out your slope, and then you know the slope of your parallel line. Okay. So try that as an exercise. And if you're going to find the line, also find the x and y intercepts. Find everything you want to know about the line. Okay. So last big topic would be looking more carefully at the slope of the line and looking at the last characterization really of the line, which is perpendicular lines. We know about parallel lines, those are slopes which are equal. What do we characterize in the slopes for perpendicular lines? Any questions so far on the equation of a line?
Nothing in the chat.
Trust me, guys, at one point you knew all this very, very well. It's a matter of dredging this out of memory. And the way to do that really is to try my little exercises. All the full solutions are at the back, right? They're here in your presentation down the bottom. You'll find all the solution slides for those exercise slides. So I do encourage you to do this at fun. That's the other thing about analytic geometry. It's very doable. It's very straightforward once you get the hang of it. There's no great mystery like with the synthetic geometry. How do I start? No, it really is kind of straightforward how you start. Of course, you need your toolbox, and underneath that toolbox is your algebra. You need to understand and be able to manipulate algebra with confidence, but it's not the great creative mystery that the synthetic geometry is. So it's kind of fun. Okay, so how do we analyze the slope of a perpendicular line? I'm going to show you a trick. Let's take our favorite, let's take our favorite triangle for a point. First of all, I'm going to take my point 1m. Clearly the slope is m. Slope is m over 1. Okay, so I'm taking a very specialized line. What is m? M is anything, any length you like. The point is the slope of my red line is m. What happens when I take the perpendicular line to that red line? I'm going to do a trick. I'm going to take the triangle and I'm going to turn it by 90 degrees. Okay, I'm going to take this value, take this line here and turn it 90 degrees and complete my triangle. I now know that this red line here is perpendicular to this line here. It's just a visual trick that if this is a right angle, that this must be a right angle because I've turned the whole thing by 90 degrees. Well, now I can figure out what this point is. Right? I'm sorry, therefore that is a right triangle because I've turned this line here 90 degrees. The whole thing's been turned 90 degrees. So I asked myself, what is this new point? If you think about it, it's minus m1. Certainly this thing has been turned m, and this thing has been turned up to 1. So there's that point. And now I ask very, very naively, well, what's the slope of that line? Well, it's 1 over minus m. It's y over x. 1 over minus m is more politely written as minus 1 over m. And that's what characterizes a perpendicular line. We have a very nice algebraic characterization of perpendicular lines. Perpendicular lines have a property that their slopes multiply up to minus 1 because m times 1 minus 1 over m is minus 1. Okay, very, very nice characterization. And that pretty much finishes the characterizations that we need to know to get started for the straight line. We have the distance formula, the midpoint formula, two very powerful equations of the general line. Y equals to mx plus b, the point intercept, the slope intercept form, and y minus y1 is equal to m times x minus m1, the point slope form. And we have characterizations of parallel lines of being equal slopes and parallel and characterizations of perpendicular lines as slopes which multiply up to minus 1, or they are the negative reciprocals of each other. They are the negative inverses of each other. That's quite a toolbox that we've developed in a relatively short period of time. And it's surprising how powerful just what we developed so far is. And I want to demonstrate this by a couple of problems with a little bit of time we have left. And I've left a bunch for you, okay? Particularly a real big one at the end. All right. So here's a nice one that I think you'll like to do. Here I've taken this line again, this line of a slope of m1. I've taken this point A of 1, comma m1, therefore it has a slope of m1. And I've drawn what I think is a perpendicular line. This blue line here is perpendicular to the red line. What is the slope? What is the slope of that blue line? Okay, we've just proven what it is. It should be minus 1 over m1. but I'd like you to prove that, okay? So I go ahead and draw a line straight down to the point B. This is the point 1, M2. Don't know what M2 is. Don't know what it is. Don't know what the characterizations of B is. I do know the X value. I've gone straight down, so it shares the X value of 1. It has some Y value M2, okay? And therefore the slope of that line, notice, is M2 over 1. Go ahead and prove that M1 times M2 is indeed equal to -1, okay? Find the distance OA, find the distance OB, find the distance AB, all using our distance formulas, and then show that if that is a right angle, if you do have a Pythagorean relationship, then truly M1 times M2 is equal to -1. A very nice proof. You'll like this proof if you give it a try. Just reproves in a different way what we've just shown. Here's another one for you to try. Here's a theorem right out of Euclid. If you have a isosceles triangle, it will be the two equal legs. Here's the base. If you have an isosceles triangle and you drop the line down to the midpoint of the base, that midpoint will be perpendicular. That line dropped down will be perpendicular to the base. Okay, if it is the midpoint, then that must be perpendicular to the base. Euclid even proves more. Turns out that these two angles also must be equal. This line, not only if you drop it to the midpoint of an isosceles triangle, not only will it be perpendicular to the base, but these two angles, in fact, will be equal, that this is a bisector of the angle. Again, I've kind of given you the steps to think about. First of all, you want to demonstrate. Here are real points here. We've got some real numbers here. Show that this is an isosceles triangle. Okay, use your distance formula to convince yourself that these two line segments are equal. Find the midpoint, okay, using the midpoint formula, and then show that this line here, PM, is in fact perpendicular to this line here, QR, and prove algebraically Euclid's theorem. Okay, I think the last thing I want to do is the perpendicular bisector of a line. One more thing. I think we have just enough time to do this. The perpendicular bisector of a line segment. Here I have two real points, P and Q, and I'd like to find the equation of the line that goes through the midpoint M and is perpendicular to that line. Okay, but really this is a very nice example of how straightforward analytic geometry can be. Just think about this problem for 10 seconds here, guys. What do you want? You want the equation of a line that goes through M and is perpendicular to the black line PQ. So you want the slope and you want a point. That's the point slope formula. You're asking me for the very two things I need to characterize, to write down the equation of a line. A point and the slope. Well, the point comes from the point slope, from the midpoint formula. The slope comes from the slope of the line I gave you, right? Get the slope of PQ and take the negative inverse. You have the point, you have the slope, you write down the point slope formula. And from that, you can certainly derive the slope intercept formula. That's exactly what I've done here. That is exactly what is here. And I went ahead and calculated the two intercepts. Okay, that's all I've done. I've done an algebra, very simple algebra for you guys, very simple algebra for those steps. What, you're looking for a point in the slope? Okay, I can get a point in the slope. That's the straightforwardness of the analytic geometry, as opposed to, finding the equation, finding the characterizations of the perpendicular bisector through synthetic geometry. And that's the next to last little exercise I have for you. Isn't it true that the other way to characterize the perpendicular bisector, the way we characterize, in fact, in Euclidean geometry, it is the locus of all the points which are equidistant from the endpoints. The perpendicular bisector line has the property that any point on that line must be equidistant from the two endpoints. It makes a whole series of isosceles triangles, including the midpoint of the line, because it certainly is equidistant from the endpoint. There is the entire locus of the line. I asked you to use that idea that any arbitrary point xy, I called it just point z, okay? Any arbitrary point xy, if it has the property that it is equidistant from -3, 2 and the point 5, 6, you will generate the characteristics of a straight line. The very straight line, very same straight line as the previous slide. This is also a fun theorem to do using our distance formula. A completely different characterization of the locus by using the distance formula as opposed to a point and a slope. Okay, so those are the general exercises I'd like you to try. And oh, I'm sorry, I did have one more thing, which is just the intersection of two lines. Here we have two lines, and this is something we know all about. How do we find the intersection of two lines? We've been doing this for weeks, right? It's just two equations and two unknowns. Using our substitution method, we'll go ahead and get the intersection of the line. Okay, there is one more thing I wanted to do. Okay, so we will stop here. There's one more thing we wanted to look at on this intersection thing, which we'll finish up next week. Okay, so we hopefully limped through fairly well in terms of my sound. Before we go, any questions on what we covered so far? Not worrying about the intersection of lines. Any other properties of straight lines that we tried to cover? Are you still with me?
There's nothing in the chat, Peter.
Oh, I just came back. My video came. Okay, good. Okay, anybody want to open the mic and say anything? Okay, guys, what I'm going to do before you go, don't go. I'm going to close the. I'm going to stop recording.